Okay, there's another one. We were on 17. It was a titration of a strong acid with a strong base. And number 18, I said I was going to do 18. 18 is the same thing. A strong acid with a strong base. So 18, you solve it as 17. It's a lot of work, this homework. For you guys, it's a lot of calculations and let's go for let's go for 19. That was 18. Hold on. Okay, here we go. 19 is a little bit different. Why? Because now we have a weak acid with a strong base. And if we look the sound, okay, like I said, if we look at this, this is a weak acid with a strong base, sodium hydroxide. Let's look for a second to the titration curve, which is going to be this one. Okay, a weak acid with a strong base. You start, but there's a buffer region. Why? Because when you're getting a weak acid, remember the concept of buffer is a weak acid, for example, if it's an acidic buffer, a weak acid and its conjugate base. So in this area, you're going to have the weak acid, acid and its conjugate base. Here it is. In the midpoint, the concentration, for example, of the the acid is equal to the um, concentration of the conjugate base. Let me show you here, okay, for a second, because maybe you can't see it. If you look at this, you see here we have the acid, okay, the weak acid with the conjugate base is any. And if you, I don't know if you remember, but if you remember that we did it before, when you have equal concentration, the equation gives us that the pH is equal to the pKa because this 1 and 1, it's 1. This over this, as they are the same as 1, and the log of 1 is 0. So here you got that the pH would be equal to the pKa of the acid. Also here, this is the equivalent point. Okay, so let's go ahead and look at the data and let's go and calculate it. And let me just show you, okay, here what I was talking about, the when you got the midpoint. We're not going to do midpoint here. I don't think we have that case. But what I was talking about, the midpoint is that the pH, okay, at that point, at the midpoint, is the pKa, because we have a buffer, remember, and it would be plus the log of the concentration of the base. Let's put A minus like I was working with before, over HA. If these two are equal, this gives you 1, and the log of 1 is 0, so pH is equal to the pKa. That's what I was talking about. Okay, but I don't think we're going to do it in this exercise. I just wanted to teach you that. Let's go real quick and get rid of this. And let's start with the titration. So we got here, okay, find the pH of the titration of 20 milliliters of butanoic acid. Okay, I'm going to simplify that and I'm going to put C is 4, C4, H, too big, doesn't matter, C4, H7, Or let's do it better. Let's put it, because I like to do it like that. Sorry. Okay. So it's C3H7COOH. I wrote it like that. This is the acidic hydrogen. So we add the base, which is a strong base, sodium hydroxide, and it gives us the salt, the conjugate base of the acid, and it's going to be C3H7COONA plus H2O. Now, if we have, okay, and we're going to do it with mole like the other one, with A, we have 13.00 milliliters of 0.1 NaOH. The acid is always going to stay the same because you introduce in the flask this amount and of moles, and then it stays. The molarity is going to change depending on how much solution you add of NaOH. So let's calculate that, the number of moles of the acid, 0.0222 liters, right? 20 milliliters. One, two, I always double check. Multiplied by zero point 0.1 molar equals 0.002 moles. And that's the amount you're going to have of acid, okay, during all the whole titration. So now what we need to see, well, okay, did you use all the acid? Did all the acid react with the NaOH? So here we got 0. It was 2, right? 0.002 moles. I'm not going to put too many zeros. The answer in the right sig figs, but because it doesn't the same with the moles. Okay, so you got here 0.0, okay, moles. Now let's look at how many moles of sodium hydroxide I put in, because those are the ones that are going to react with the acid. So you got 0.013 liters multiplied by 0.1. It gives you 0.0013 moles of NaOH. So here would be 0.0013 moles. So you can see right away that we still have some acid left. So here the limiting reactant, of course, is the NaOH. Generally, the first quantity is always given less. 0 is subtract. I'm going to give you the quantities right away. Okay, this is going to be sorry, 0. Well, easy to see, 0.0070. And this, of course, is 0. Okay, and here we only found a 1-to-1 ratio. We form 0.00130. And now it's important because this is a conjugate base of a weak acid, and we're going to consider it because we have a buffer now. Okay, so we got here 0.00 moles. So like I was saying, we got how many moles of acid we have left? 0.007. How many moles of base? of conjugate base, this one. So basically what you have now is that the pH, okay, pH would be the pKa of this acid plus the log of the concentration of the base, which is C3, the conjugate base, CH7, okay, this is the divided by the concentration of the weak acid, which is COOH. But you have to be careful here again because remember we add solution, we add volume. Okay, so we have to aqueous solution. So we have to again recalculate the molarity. That's the tricky part and the majority of the work in this. So first of all, let's go ahead and do something. The pKa. The Ka, I don't know if the problem, yes, it gave it. The Ka was this. So if you do the minus the log of the Ka, the pKa would be equal to, we've done it several times, so equals to 481. Mm-hmm. 481. 4.81. That's the pKa. That's what I have. So now you got here, okay, that if the pKa is 481, we have pH equals 4.81 plus the log, but hold on. Now we have to find out the concentration of the acid and the base. Let's start with the base first, okay? And if you look at the base, the concentration of the base is the moles of the base you form, which was 0.0013, divided by the total volume, which you add 13.00 plus what you had before, 20 milliliters. So here is 0.0013. Yeah, 130 moles. And you divide it by the total volume that you have now, which is going to be the 20 initially. Let's put it in liters. 0.020 with that liters plus what you wanted added, and it was 30 milliliters, so it's going to be 0.0300 liter. So that gives me that the concentration of the base, okay, is going to be equal to 0.0013 divided by I thought it was the biggest mistake, but no, it's here the mistake, and it's not 30. I don't know if you noticed it already. It's 13 here. So it's not 30 what we add. We add, and part A is 13. Fortunately, I have my notes here, so that way it wouldn't take so long. Okay, so it's gonna be, here is gonna be 0.130 liters. Okay, here is divided by 0.033 liters, and this is moles. I'm not gonna stop with the zeros, or at the end is the sig figs. That's it. COO negative. So this is gonna be 0.03939, and this is gonna be M molar. Now we got, okay, this is a concentration of the base. Now we got to find out also the concentration of the acid, which I'm going to show you how to do it, but then you do it by yourself. Where do you get the moles of acid that you have present? Okay, you know they react already, right? And you have left is the excess of acid you have left, because you still have, and it's 0.00070. 0.12370 moles, and you divide it by, again, the same volume. In this case, zero point 0.0, we have the same volume, liters. And the concentration of the acid would be 0.08 would be equal to, this would be 0.0212. 0.0212 M. Oops, sorry. Beautiful. So now let's go back. pH, I started that up there, but it doesn't matter because it's 481. That's what I said it was, 4.81 plus log of, what do you have on top? 0. The concentration of the base, 0.039. That's the equation, remember. M, which we're going to cancel it out, divided by 0.0212. Okay, and that gives me that the pH is equal to 5.079, 5.08. Okay, which makes sense. If you look at the curve, you're going to look at it's anywhere around the buffer region, okay, and it's less, is before the equivalence point, because if you see, we still have an acid here. So it makes sense that it's around 5, should be a little bit like here. Where is it? It's 508. A little bit higher than the pK, than the midpoint. Okay, let's go with the second volume, and it's 20.6. Okay, so if you have C3H7COOH plus NaOH gives me C3H7COO Na. Now, what I'm going to do, I was thinking, is just leave that like that. You know the reaction already. So, but I wanted to, initially acid, you got the same thing, which is 0. All the time. It's the same, 0.002, the initial of the acid. Now here you're going to have a different amount because you add 20, and it's going to be 0.0260, right? And multiply by 0.1 is going to be 0. The moles, right? By 0.1 molar and this is liters, is going to be 0.002060 moles of NaOH. So we're going to put here 0.002060, just by a little bit, but this is higher. So now you went over the equivalence point. So you're going to have here, this is going to be the limiting reactant, 0.00200. This is 0, so you're going to have a little bit more of base. So it's here 0.4 zeros. 1, 2, 3, 4, 6, 0, 0. And this is the moles of NaOH. Now this is a strong base. So you have nothing here from that is going to be, you know, just what you're going to do is find the concentration of OH. How? Is the concentration of the NaOH in excess. And it's going to be your number of moles of excess, right, of NaOH, which is the same as the OH, a strong base, and you divide it by the total. And the total would be 20.60 milliliters, and you already had 20 of, I'm giving the answer already, 20 of acid, so it's going to be 4060 milliliters. So it's going to be 0.04060 liters. So the concentration of OH hydroxide equals 1.4778. 1.4778 times 10 to the negative 3 molar. So the POH is the minus log of this. Remember, we have an excess now. And then equals, the POH equals the minus log of that, which is going to be 2.83. And the pH would be 14 minus 283. It's going to be 11.77, I think so. No, 17. 11.17. I got it written, but I can't read now. So here we got the pH. Now the last one is very similar. Exactly. Almost the same as the other one. Let me just get started with that and leave you till you finish. And it's basically the same one. That it's 29, right? And it's going to be, the only difference is that you got from the acid, you got 0.0020 moles. And the NaOH, you're going to have 0.0029, because remember, you've multiplied by, so it's 2 zeros, 29, 0 moles. So you know you got an excess of NaOH. And what is the excess? Once you get an excess of NaOH, remember, it's a strong acid, and that's what you're going to have in the solution, hydroxide. Okay, and if you look at the pH, well, hydroxide in bigger amount is a basic solution. So if you subtract this, that's the only difference from the part B. It's going to be 0.0009. 90 moles. And from there, you do the same thing. But the total volume would be the 29 plus, of course, what you got initially of the acid, which was 20. So the total volume would be 49 and you do zero point 0.00 and you do the same thing. Divide this, find out the concentration of OH and find out the POH and then the pH. Finish that. I don't know if you remember question number 5. I said that I was going to do it. And because of question number 5 is the titration of a weak acid with a strong base, just what we were doing right now, I save it for now. And you have to label it. And if you see, this is already labeled. The midpoint, like I was talking, is around here. Then you have the pKa, which is going to be here, equals, remember, here. Okay, here is going to be the buffer region, all this. The equivalence point would be here. It's not difficult once you, and if you look at your PowerPoints, at the PowerPoints I posted, you see those are the ones. You see pKa of the weak acid, 4 HPR of the acid. I was looking at phenolphthalein. Sorry, is 4.89. And this is going to be, this is a specific example, and this is going to be the equivalence point and the, you see, and this is going to be the excess of hydroxide.